Okay, so now that we've taken a little bit of a look at moles, next video we're going to be looking at how we can use moles to figure out the formulas. So we do need to know a little bit about the different formulas that we can report in chemistry. So when we're talking about structural formulas, they give us the most information, and it's basically a picture that shows how atoms in a molecule are connected. So a structural formula is similar to a Lewis structure in that it shows how many electrons there are between atoms and how those atoms are connected within a molecule. So for example, if we have two electrons, one pair, then we draw a line between the two carbons to show that they are connected by one bond or two electrons. If we have four electrons that are holding together the nuclei of these two carbon atoms, again, then we'll draw these two lines to represent a double bond. This should be relatively familiar to you as we've been doing a lot of Lewis structures. Now these structural formulas can get quite complicated. Here I am drawing a much larger molecule, and as you can see, structural formulas start to be very important as we get larger molecules so that we can see where all of our atoms are located. With a little bit less information, we can talk about molecular formulas. So instead of showing exactly how atoms are connected, they basically just report to us the total number of atoms in a molecule. So for example, H2S, CO2, C6H12O6, which is glucose for you, those of you in biology, those all show how many atoms there are in a molecule. So in glucose, there's 6 carbons, 12 hydrogens, and 6 oxygens. Now, just FYI, in organic chemistry, we have a convention where we always write carbon first, then hydrogen, then nitrogen, then oxygen. That's just the order for organic compounds. We'll take a much deeper look at this when we take a look at organic chemistry. And again, to be able to switch between structural and molecular, all you have to do is count how many atoms there are and report it in the formula. Now to go back the other way, to go from molecular to structural, we can't unless you know spectroscopy, which we'll take a look at next year, but right now we're going to just leave it as we can. Now, empirical formulas give us the least amount of information. They tell us the simplest ratio of elements in a molecule. So for example, if we have the molecular formula of H2O2, so hydrogen peroxide, agua oxigenada, very commonly used to disinfect things, the empirical formula of this molecule is HO. It's a 1-to-1 ratio. The simplest ratio is 1-to-1. And so the empirical formula is HO. If we have an empirical formula of O, then our molecular formula can be any of the O2, O3, or 4, or 5, etc. Taking one last look at another example, so we have glucose there, and again the empirical formula is CH2O because it's a 1-to-2-to-1 ratio. Now to go from that molecular formula to the empirical formula, we divide by the highest common factor, so HCF. Here I'm going to do the example again with glucose. Here we have 6, 12, 6 as a ratio. The highest common factor here is 6, so we divide each of those numbers by 6 and we get a 1-to-2-to-1 ratio, CH2O. And again, hopefully you can see why we call these carbohydrates, as their empirical formula involves carbon and a water. Now, in order to go the other way from empirical formula to molecular formula, you need molar mass, which we'll take a look at next class. The last type of formula that I would like to introduce to you is this idea of skeletal formulas. This is very commonly depicted in chemistry in the media. And it's this idea that a lot of organic chemistry has carbon and hydrogen everywhere. So you have a molecule and it's mostly carbon and hydrogen. So what we can do is we can simplify carbon and hydrogen to make the structures more readable. Here I'm going to show you how to go from a full structural formula to a skeletal formula and back. So watch very carefully. Here I have my full structural formula. It's showing all of the atoms, all of their connections within the molecule. As you can see, it's quite tedious to draw, and we don't want to have to draw this multiple times if we're trying to draw a reaction process. So what we do first to get to that skeletal formula is we remove all of the hydrogens connected to a 4-bonded carbon. So you take a look at the hydrogens. If they're connected to a 4-bonded carbon, so if carbon has 4 bonds, you remove them. So that's what I did in that second step. My third step, it's a little bit tricky to wrap your head around, so take a look very carefully. We basically replace all of the carbons with points. So it's a little hard to describe, but take a look. I'm replacing all of the carbons that I see with points. So I'm going to go ahead and highlight them so you can see I've replaced this red carbon with that point, and as you can see I can go along and I can show you what each of the points correspond to in terms of carbon. So now all I have is everything but carbon and hydrogen bonded to carbon. This is a lot easier to draw multiple times, and so it's what we use normally to draw organic compounds. Let's try going the other way. So here I have a skeletal formula and I want to draw a structural formula. The first thing that we do is we add carbons back to the points. So every time that you see a point, you add a carbon, keeping in that double bond that you can see in that skeletal formula. The final step to get to that full structural formula is that we want to add hydrogens until all carbons have 4 bonds. So again, I'm going to redraw what I did in my first step, and then I'm going to add hydrogen until each carbon has 4 bonds.